welcome to the deep dive.
Yeah.
So, today, September 16th, 2025, it's one of those dates that really links up a couple of fascinating things in space.
Right. There's something cool you can actually see right now.
Exactly. Like right now in the pre-dawn sky, you've got the crescent moon shining near Jupiter in Gemini. It's pretty neat.
But today also has this connection to, well, a tougher moment from way back in the early days of spaceflight.
Yeah, a more somber note. And that kind of sets up our mission for this deep dive, taking you through the absolute latest, most interesting things happening out there.
From, brand new rocket engines to defending the planet, amazing sights in the sky, even how we're tackling space junk.
Yeah, it's all connected.
We want to get you up to speed fast, connect those dots, maybe give you a few aha moments.
And that's the thing, isn't it? These stories, they're not isolated. Each breakthrough, each challenge, it all feeds into this bigger story of us trying to explore, understand,
And importantly, protect our little spot in the universe. Absolutely. From the tech taking us further to keeping our orbital paths clear, it's all part of this grand unfolding narrative.
Okay, let's kick off with something that really could be a game changer. Seriously. Imagine quadrupling a rocket's payload.
Not just bigger rockets, but changing the whole equation.
Right, and it's not just theory. We're talking about the rotating detonation rocket engine, or RDRE.
It's a totally different way of thinking about rocket thrust. Unlike regular rockets with that steady flame,
Yeah.
RDREs use a detonation wave. Think of it like a controlled explosion that just keeps racing around a circular channel.
Okay, wow, like a continuous sonic boom inside the engine.
Sort of, yeah, a continuous series of these high-pressure bursts. And that makes it incredibly efficient. We're talking maybe a 15% jump in efficiency.
Which translates to?
Nearly quadrupling the payload. It's huge. And this idea, it's been around since the 50s, believe it or not.
But it wasn't possible back then.
Not really. We needed things like modern 3D metal printing for quick prototypes and these super high-speed cameras like 1 million frames a second just to see what was happening with the detonation.
And the people involved now, Pam Melroy, former NASA deputy administrator, space shuttle astronaut, she's joined the board of Venus Aerospace, the company doing this.
That's a huge endorsement.
Totally. She literally said, the efficiency jump of RDREs is really a game changer for launch and for other applications. When she says game changer.
You listen. And Venus Aerospace, they're thinking big, launch vehicles, obviously,
Yeah.
but also orbital transfer vehicles like space tugs.
Aha, moving satellites around.
Exactly. And landers, too, for the moon or Mars. The really ambitious goal, though, the Stargazer M4,
Which is?
a Mach 4 passenger jet. San Francisco to Tokyo in, wait for it, 2 hours.
2 hours. Okay, that's incredible.
And Melroy also pointed out, this isn't just about speed. It will have a huge economic impact for the United States. It's about changing global access.
So beyond just super fast flights, this tech has massive implications for deep space, like getting to Mars or the moon more easily.
Definitely. Because current big players, like, say, SpaceX's Starship, they rely on cryogenic fuels, super cold liquid oxygen, and methane.
Right, and you get that boil-off problem on long trips. The fuel evaporates.
Exactly. But RDREs, they don't need those cryopropellants.
Yeah.
And they don't need those huge engine bells you see on traditional rockets.
Which makes them.
Much better suited for long trips for operations on the moon or Mars. It really opens things up.
Speaking of Mars, this connects to an old mystery, doesn't it, from the Viking missions?
It does. Back in the 70s, the Viking landers did these experiments looking for organic molecules in the soil. The building blocks of life, basically.
And they found.
Nothing. Zero. Which was really puzzling. It made Mars seem completely sterile.
But that wasn't the whole story.
Well, fast forward to 2008. The Phoenix lander finds perchlorate in the Martian soil.
Perchlorate.
Okay. Yeah, and the leading theory now is that when the Viking experiments heated up the soil samples, this perchlorate actually chemically destroyed any organic compounds that were there.
So the experiment itself might have wiped out the evidence.
Potentially, yes. It's a neat explanation for why Viking got those negative results, even if organics were present.
Okay, from Martian mysteries to something you can look forward to seeing. That asteroid, Apophis, is coming up in just a few years.
It is. April 13th, 2029. Mark your calendars. It's a Friday the 13th, actually.
Yeah, of course it is. And this is a big one.
Oh, yeah. About 340 meters across. And it's going to pass incredibly close to Earth. Closer than our geosynchronous satellites.
Closer than the weather and TV satellites. Wow. How close are we talking?
About 31,000 kilometers, or 5.9 Earth radii, which is really, really close for an asteroid this size. An event like this only happens, on average, maybe once every 7,500 years.
And the amazing part is, people will actually be able to see it.
Yeah, potentially up to 2 billion people. Anyone in Africa or Western Europe, under clear, dark skies, might see it as a point of light moving across the sky. Naked eye.
2 billion people. Richard Binzel from MIT said something about that, right?
He did. He said this is 4 times more people than saw Neil Armstrong walk on the moon. Think about what a world event this is going to be. It's going to be huge.
But scientifically, it's more than just a show, right?
Absolutely. Scientists are calling it an unprecedented natural experiment. We get to see how Earth's gravity, maybe even our magnetic field, affects Apophis as it flies by.
Which helps us understand asteroids better and maybe defend against dangerous ones.
Exactly. It's crucial data for planetary science and planetary defense. And there are missions lining up to study it. NASA's OSIRIS-APEX is already on its way.
Already heading there. Cool.
Yep. And Europe's Ramses and Japan's Destiny Plus should launch around 2028 to intercept it too.
But just to be crystal clear,
Yeah.
it is going to miss us, right?
Yes. Binzel, NASA, everyone is very clear. Apophis will safely pass the Earth. This is purely an observation opportunity, not a threat.
Okay, good. Phew. So while we wait for 2029, there's a more regular show coming up soon, the Orionids.
That's right, the Orionid meteor shower. These are bits of debris left behind by Halley's Comet.
The famous one.
The very same. The shower is active from late September to late November. But the peak this year is October 20th and 21st.
And is it a good year for them?
Should be excellent, actually.
Ah.
The moon will be new, meaning dark skies, perfect viewing conditions, hopefully. And these meteors are fast 41 miles per second, or 66 kilometers per second. So you get these quick, bright streaks.
Nice. And there are other things to look out for in 2025, too.
Yeah, a few highlights. The next full harvest moon is Monday, October 6th. We also get 2 total lunar eclipses this year, March 14th and September 7th.
Eclipses are always cool.
Definitely. And 2 partial solar eclipses as well, March 29th and September 21st. But like we said at the start, right now, today, September 16th, look for that crescent moon and Jupiter pairing up before dawn. A nice little celestial sight.
Okay, let's shift gears from looking out there to looking, well, right above us. The problem of space junk.
Yeah, it's becoming a serious issue. We've got something like 14,000 tracked pieces of junk whizzing around in low Earth orbit.
And that's a danger to satellites, the ISS.
A major hazard. It's really tricky. Most conventional ideas, like robotic arms or nets, struggle because the debris is often tumbling unpredictably. Trying to grab something spinning wildly at orbital speeds is difficult.
So we need smarter solutions.
Which brings us to this really cool idea from Tohoku University in Japan. Kazunori Takahashi's team.
What are they doing?
They've developed a non-contact method. A bidirectional plasma ejection type electrodeless plasma thruster.
Okay, break that down.
Oh, yeah.
Yeah.
Basically, it's a satellite that shoots out beams of plasma ionized gas. It has 2 thrusters pointing opposite ways.
So they cancel each other out. The satellite stays put.
Precisely. It holds its position. Then it can fire a targeted plasma beam at a piece of debris. It doesn't touch it, just gives it a gentle nudge with the plasma.
Just enough to slow it down.
Just enough to make it dip lower into the atmosphere, where it eventually burns up safely. They think they can deorbit a 1-ton piece of junk in under 100 days using just a few kilowatts of power. And using argon gas makes it cheaper.
That seems incredibly clever. Non-contact is key.
And there's another approach, too, from the European Space Agency, ESA. They're using lasers.
Lasers to zap space junk.
Not quite zap it, but to nudge it. They have these laser ranging stations in Spain, in Zanya 1 and Megas 2, that are already really good at tracking debris.
Okay.
The plan with Zanya 2 is to use the laser to gently push the debris with photons, light particles. Just impart a tiny bit of momentum.
Enough to change its orbit slightly. Avoid a collision.
Exactly. It means active satellites don't have to use their own limited fuel to dodge junk. They call the project OMLET.
Omelette, like the breakfast?
Yeah. Stands for Orbital Maintenance via Laser Momentum Transfer. Basically, a space traffic cop using lasers.
That's brilliant.
And interestingly, this same laser tech might also be used to test quantum encrypted communications, so a double benefit.
All right, from cleaning up our orbit to enjoying some natural wonders, let's talk auroras. The northern and southern lights, what actually causes those amazing displays?
It's all down to the sun, really. Charged particles streaming off the sun, the solar wind, interacting with Earth's magnetic field and our atmosphere.
So particles hit the atmosphere and make it glow.
Pretty much. The big drivers are usually coronal mass ejections, or CMEs, these huge eruptions of plasma from the sun, or sometimes high-speed streams of solar wind pouring out of coronal holes.
Gaps in the sun's atmosphere.
Yeah, areas where the sun's magnetic field lines open up into space, letting particles escape easily. Strong solar flares can add to it, too.
So if it starts at the sun, how do we know when we might see auroras down here? How does the forecasting work?
It's complex. Scientists monitor a few key things. One is the KP index. Think of it like a scale from 0 to 9 measuring global geomagnetic activity.
Higher CAPE means stronger aurora, maybe seen further south.
Exactly. But another crucial factor is the BLES component of the interplanetary magnetic field, the magnetic field carried by the solar winds. If that BLES component points strongly southward, it connects really effectively with Earth's own magnetic field, which points north. It's like opening a door, letting way more solar particles flood into our atmosphere.
Ah, so a south breeze is good for auroras.
A strong south breeze is often the key ingredient for a really good show. Agencies like NOAA's Space Weather Prediction Center and the UK Met Office track all this stuff constantly.
And there's a timing thing too, right? Like certain times of year are better.
Yeah, there's this fascinating seasonal effect called the Russell-McPherson effect. Basically, around the equinoxes, March and September, Earth's tilt makes our magnetic field align more favorably with the solar winds.
So it's easier for those particles to get in.
Kind of like temporary cracks open up in our magnetosphere more easily.
Right.
So you often get stronger and more frequent auroras around the equinoxes, even with moderate solar activity.
We saw some big ones recently, didn't we, in 2025?
We did. There was a severe G4 storm back on June 1st. That pushed auroras way down into mid-latitudes. People saw them in Northern California, New Mexico.
What?
And another strong one, a G3 on May 29th. That one lit up skies as far south as Italy, around 45 degrees north. So yeah, keep an eye on forecasts, especially near the equinoxes.
Incredible. Okay, let's jump from our atmosphere way out to the very early universe. The James Webb Space Telescope keeps finding weird stuff.
Huh. Yeah, that's one way to put it. It's been seeing these tiny, very distant little red dots. The initial thought was, wow, these are surprisingly mature galaxies forming incredibly early.
But maybe they're not galaxies.
While there's a new, really bold theory gaining traction. What if they're not galaxies at all, but black hole stars?
Black hole stars, what does that even mean?
Okay, stick with me. Imagine a giant cloud of primordial gas collapsing. But instead of igniting nuclear fusion in the core like a normal star, it's collapsing around a supermassive black hole that's already there.
So the black hole is powering it, not fusion.
Exactly. The gas falling into the black hole heats up immensely, making this huge object shine incredibly brightly, mimicking an early galaxy.
And why is that idea important?
Because it could solve a huge puzzle. How did supermassive black holes get so big so fast in the early universe? If they started inside these black hole stars, feeding voraciously from the beginning, well, that could explain it. It potentially flips our understanding of how the first large structures formed.
That's mind-bending stuff. From the edge of the universe, let's come back much closer and back in time again to today's date, September 16th, but in 1949. A very different, quite poignant moment in space history.
It really is. On this day in 1949, the U.S. launched a captured German V-2 rocket. But its payload wasn't scientific instruments. It was Albert III, a long-tailed macaque monkey.
Part of those early animal tests to see if spaceflight was survivable?
Exactly. Trying to understand the effects of acceleration, weightlessness, the brutal realities of launch, but it ended tragically.
What happened?
The rocket exploded just 10 seconds after liftoff. Albert III was killed instantly.
Oh, that's awful.
And he wasn't the first. Albert I and Albert II, earlier monkeys, also died in V-2 tests. It just underscores the immense dangers and the, well, ethically challenging path they took in those very early days.
Were any successful early on?
It took time. Animal testing largely stopped in the 80s, but it wasn't until 1961 that a test monkey named Albert VI, actually, finally survived a launch and recovery. It shows just how hard-won every step was.
That really puts things in perspective. Even today, with all our technology, rocketry is still incredibly challenging, like the Firefly Aerospace failure earlier this year.
Right. Their Alpha rocket failed on April 29, 2025. They traced it back to extreme heat caused by the rocket's plume interacting with the airflow, made worse by a steeper climb than usual.
But they figured it out.
They did. They identified the cause, made corrections, and crucially, they've already been cleared to resume launches. It shows the resilience, Learn from failure, fix it, fly again. It's the nature of the business.
And that feels like a good place to wrap up this deep dive. Wow, we covered a lot of ground today.
We really did.
From those potentially revolutionary RDREs changing how we get to space, maybe even how we travel around Earth.
We'll go digging into Mars's past, figuring out those Viking results.
Predicting auroras, getting ready for Apophis's flyby.
Tackling space junk with plasma and lasers.
Peering back at the universe's baby pictures with Webb, and remembering those tough early steps with Albert III.
It really highlights how interconnected it all is. Every discovery, every setback, it pushes us forward, raises new questions. Our picture of the universe is constantly being updated.
Absolutely. Which leads us to our final thought for you. What new natural experiment like Apophis, or what completely unexpected breakthrough, maybe like those black hole stars, will redefine our understanding of the cosmos tomorrow? And how will you be ready to dive in when it happens?